8A.Properties of fluids. 8.1 Introduction. Tsunamis can be explained by the mechanical forces exerted by air and water. Chapter 6 describes how moving objects possess energy, and Chapter 7 explains how forces acting on objects can do work. Fluids can exert forces and do work too. Because of the special physical properties of fluids, such as their lack of rigidity, physicists have established a distinct area of study within mechanics called fluid mechanics. Fluid mechanics is the study of how fluids flow and how forces and energy are transmitted through fluids. Both liquids and gases flow and assume the shape of their containers. Matter that has these properties is called a fluid. Fluids exert pressure, which allows them to transmit forces. They exert an upward force that acts against the force of gravity on any immersed part of an object. In this chapter, you will learn how motion, forces, work, and energy apply to liquids and gases. 8.2 Pressure. While riding in a car on a trip through mountainous terrain, you perhaps have experienced a sharp pain in your ears that is relieved only by swallowing. This condition is caused by a rapid change in air pressure against your eardrum. These abnormal forces on the delicate eardrum membrane can cause great discomfort. So what exactly is pressure? The pressure, P, on a surface, is a ratio of force to area, the net force acting perpendicular to the surface, and the area over which it acts. Pressure is calculated using the formula P equals F over A, where P is pressure in newtons per square meter. F is the net force acting perpendicular to the surface in newtons, tons, and A is the total surface area over which the force is applied in square meters. The larger the area over which a given force is distributed, the lower the pressure. For example, suppose you place a book flat on a table. The book exerts 10 N on the table. The book's cover has an area of 580 square centimeters, 0.058 square meters, and the pressure the book exerts on the table is distributed over this area. P equals F over A equals 10. N over 0.058 meters square. P about 170 newtons per square meter. Now take the same book and balance it on top of a short piece of dowel rod 2.5 centimeters in diameter. The dowel's cross-sectional area is calculated as A equals PIR square, about 4.9 centimeters square, or 4.9 times 10 to the negative 4th power meters squared. The pressure exerted on the table by the book through the dowel is now distributed over this smaller area. P equals F over A equals 10.N over 4.9 times 10 to the negative 4 power m squared. P about 20,400 newtons per square meter. Fluid pressure. In the book dowel example, the only pressure exerted was the vertical weight of the book on the surface area in contact with the table. Pressure was not exerted in any other direction because solid, rigid objects can transmit a net force in only one direction. With liquids and gases, the situation is somewhat different. Imagine that you could isolate an exceedingly thin horizontal slab of water with an area of 1 square meter in the center of a still swimming pool. See figure 8-4. We know by Newton's first law of motion that if the water in the slab is not accelerating, all forces acting on it must be balanced. In particular, the downward force above the water slab must equal the upward force below the slab. Since both forces act on equal surface areas, the pressures above and below the slab must be equal. Now, rotate the imaginary slab 90 degrees. The same conditions exist. The horizontal forces, and thus the pressures on both sides of the vertical slab, are equal. Because it does not accelerate, we can conclude that at a given point in a body of water, the pressure is exerted equally in all directions. This property of fluids is called fluid pressure. Fluid pressure exists because liquid and gas particles are not held rigidly in place. The kinetic molecular model of matter says that the particles of matter, especially in fluids, are in constant random motion. When a force is exerted on a fluid particle, it transmits the force in the direction the particle is moving. Because of the innumerable randomly moving particles, the force is transmitted equally in all directions. Units of pressure. In the SI, Pressure is measured in newtons per square meter, N per m squared, or with the Pascal, the derived SI unit, for the same quantity. This unit is named after the prominent 17th century philosopher and physicist Blaise Pascal. 1 Newton per meter square equals 1 Pascal. There are also other units of pressure. The average atmospheric pressure at sea level is 1 atmosphere, ATM. 1 atmosphere is 1,1325 pounds. Scientists define the bar, B, as being equal to 100,000 pascals to make studying the atmosphere easier. Average atmospheric pressure, 1 atmosphere, is slightly higher, 1.013 bar. Meteorologists today report air pressure in millibars, MB. The bar is no longer used in most scientific measurements. Factors affecting fluid pressure. Fluid pressure may exert itself equally in all directions at any specific point in a fluid, but that doesn't mean that the pressure is equal throughout the fluid. Pressure can change greatly within a fluid. That is why you feel pressure in your ears when changing altitude in a plane or changing depth in the water. Under natural conditions, gravity and fluid properties determine the pressure at a given point in the fluid. Fluids have weight because every fluid particle has a mass that experiences the pull of gravity, W equals mxg. Each fluid particle exerts its weight on surrounding particles, as Newton's third law predicts. That force, or weight, is transmitted downward through the fluid. Thus, the deeper the volume of a fluid, the more weight is experienced at the bottom of the fluid and the higher the pressure. For example, the Earth's surface is at the bottom of its atmosphere, so the maximum pressure in the atmosphere is experienced there. As one goes higher in elevation, there is less air above, so air pressure decreases. Similarly, water pressure is 0 at the surface of a body of water. As one goes deeper, the amount of water above increases, and so pressure increases with depth. The rate of pressure increase in water is approximately 1 atmosphere, 14.7 pounds per square inch, for every 10 meters, 33 feet of depth. Deep water instruments and submarine vehicles must be designed to withstand the high pressures of deep depths. The volume or shape of a fluid's container does not affect the pressure at a given depth or height in the fluid. For example, the water pressure at a depth of 10 centimeters is essentially the same in a glass of waters in the Pacific Ocean. Water pressure depends almost entirely on the water depth. Water pressure due to depth alone is called hydrostatic pressure. Fluid density is another factor that determines fluid pressure. When particles are closer together, the weight they exert for a given change in depth or height is greater. The effect of gravity on liquid density is fairly insignificant because liquids are nearly incompressible. Therefore, the increase of density with depth in liquids is insignificant. Water temperature and dissolved matter are more important factors in determining water density. For example, cold water is denser than warm water, and salty water is denser than fresh water. Overall, depth is the most important factor controlling hydrostatic pressure in liquids. Atmospheric gases are highly compressible. Air molecules closer to the Earth are more strongly attracted by the Earth's gravity than those higher up. As a result, the Earth's gravity hugs the blanket of air closely to the surface. Air density and atmospheric pressure decrease rapidly with increasing altitude. Half the matter in the atmosphere is below 5.5 kilometers, and 99% of the atmosphere is below 32 kilometers. Nearly all the atmosphere is below 47 kilometers, 29 miles. Because temperature affects the volume of a gas much more than it affects the volume of liquids, temperature also has a much greater effect on atmospheric density than on water density. The pressure differences between cold and warm air masses can vary up to 10% of total atmospheric pressure. Pressure instruments. Nearly every pressure instrument is designed to compare a measured pressure to a known pressure. The earliest accurate pressure instrument, built by Evangelista Torricelli in 1643, measured atmospheric pressure. Torricelli's mercury barometer consisted of a thick-walled glass tube filled with liquid mercury and sealed on one end. When the tube was upended in a bowl of mercury so that air wouldn't enter the tube, the level of mercury in the column dropped a short distance. At that point, the atmospheric pressure on the mercury in the bowl equaled the weight of the mercury in the column. The height of the mercury column, about 760 millimeters, was proportional to atmospheric pressure. The vacuum in the sealed end of the tube was the standard to which atmospheric pressure was compared. The pressure indicated by a mercury barometer is sometimes called absolute pressure because its standard is a vacuum, a condition of zero pressure. Modern aneroid barometers are more compact than the meter-long mercury barometer. Aneroid barometers contain a sealed accordion-like can filled with a low-pressure gas. The can, which flexes with changing atmospheric pressure, is linked to a pointer through a gear mechanism. It uses the gas pressure within the flexible can as its standard. Digital barometers rely on an aneroid mechanism to sense the air pressure and convert the flexing motion into a digital signal. Fluid pressures in mechanical systems and pipes are measured with mechanical gauges. These instruments are built around a flexible sealed can, or a sealed tube, that is bent into a U or a coil. As fluid pressure increases, the tube unbends or the can expands, moving a mechanism attached to an indicator. The reference zero pressure for these instruments is set at atmospheric pressure. So when the gauge indicates exactly zero pressure, it is actually measuring atmospheric pressure. Gauge pressure in a system equals the absolute pressure in the system minus atmospheric pressure. Some pressure-sensing instruments use a C-shaped sealed tube detector called a Bourdon tube. A Bourdon tube senses changes in pressure by flexing as fluid pressure changes inside the tubing. Unlike other pressure instruments, Bourdon tube instruments are very rugged and suitable for extreme environments. 8.3. Using fluid pressure to solve problems. 9 years before the Indian Ocean tsunami in 2004, the United States National Oceanic and Atmospheric Administration, NOAA, began installing special instruments in the Pacific Ocean. These instruments are designed to detect passing tsunamis that could threaten the United States and other countries around the Pacific Basin. The sensors, called tsunameters, are placed on the bottom of the ocean with anchors at depths of 1,000 to 6,000 meters. As a tsunami passes overhead, the sea level changes less than a few meters in deep water. Tsunameters use a Bourdon tube pressure detector to measure the tiny change in sea pressure. Its sea tube straightens slightly as it expands in response to the pressure rising inside it. The free end of the sea tube moves a digital sensor, whose data is analyzed by a computer. When a tsunami is detected, an acoustic signal is transmitted like sonar through the water to a buoy on the surface. The buoy sends an alerting radio message to an overhead satellite, which relays the alert to a tsunami warning station. Because of the 2004 Indian Ocean tsunami, the United States moved quickly to complete its Pacific Ocean system of 32 buoys and to expand tsunami warning coverage to the Atlantic Ocean and the Caribbean Sea. Japan received alerts from the Pacific system in 2011, but the earthquake was so close to shore that little time was available to move people away from the danger areas. Southeast Asian nations are now seeking to install a similar buoy warning system in the SEI's mildly active waters surrounding them to provide needed alerts. 8.4 Buoyancy. While playing in the family pool, 10-year-old Beth asked her dad to pick her up and throw her back into the water. He quickly discovered that it was easy to pick her up partway, but as he lifted her out of the water, she became heavier and heavier. His plan of flinging her halfway across the pool was quickly reduced to merely tossing her a few feet. At first she was so light, but she apparently gained weight as she came out of the water. What happened? Objects weigh less in water or other fluids than they do when they are not immersed. Archimedes explained this observation in the 3rd century BC. He learned that when an object sinks into water, it displaces a certain volume of water. He reasoned that the displaced water has weight and exerts a force on the immersed object. Archimedes' principle states that an immersed object is lifted or buoyed up by a force equal to the weight of the fluid displaced. This lifting force is called the buoyant force and applies to floating as well as submerged objects. In general, the densities of a fluid and an object immersed in it will likely be very different. So the amount of fluid displaced by a completely submerged object has a different weight than the object itself. Thus, the buoyant force of the displaced fluid will not equal the object's weight. Whether an object will float or sink depends on how much buoyant force is generated by the volume of fluid the object displaces. If the buoyant force is greater than the object's weight, the object floats. If it is less than the object's weight, the object sinks. Suppose you immerse a block of pine in water. The density of water is 1.0 grams per cubic centimeter, while the density of pine wood is about 0.5 grams per cubic centimeter. Will the block float? The volume of displaced water will weigh twice as much as an equal immersed volume of the pine block. According to Archimedes' principle, only half the wood's volume needs to be immersed to generate a buoyant force equal to the entire weight of the block of wood. The block floats. Now suppose you immerse a lead sinker, density equals 11.3 grams per cubic centimeter, in water. No matter how much of the sinker is submerged, it will always weigh much more than the buoyant force of its displaced volume of water dot. Without any other forces to support it, the sinker will accelerate to the bottom, Newton's second law. Hence the name sinker. You may be wondering, since steel has a density much greater than water, why a steel ship floats. The density of an entire ship is not equal to the density of the steel used to construct it. Its density is determined by dividing the total mass of the materials in the ship by the structural volume of its hull, which is mostly air. A ship is not simply a block of steel. The naval architect's goal is to design a ship whose overall density is much less than that of water, so that the ship floats. Gases are governed by the principles of buoyancy too. Helium-filled balloons float upward because the helium in them is less dense than the surrounding air. Helium balloon displaces air, and the resulting buoyant force of the displaced air is greater than the weight of helium and the balloon. Hot air balloons operate similarly because the internal hot air is less dense than the cooler surrounding air. Sometimes the weight of an object exactly equals the weight of fluid it displaces. This happens when the object and the fluid have the same density. The object's weight and the buoyant force cancel each other exactly, and the object is suspended in the fluid, neither rising nor sinking, Newton's first law. Dirigibles, hot air balloons, submarines, and many aquatic organisms are able to adjust their densities so that they nearly match those of the surrounding fluids. These objects and organisms seem to float effortlessly within their media. 8.5 Specific gravity. Scientists and engineers have established a way to compare the density of a substance with the density of water. This comparison is called relative density, or specific gravity, SG. A substance's specific gravity is a unitless number obtained by dividing the density of the substance by the density of water. Since water's density at standard conditions is 1.0 grams per cubic centimeter, the specific gravity of a substance is simply the numeric value of its density without the units. For example, the specific gravity of pine wood is calculated as follows: Sg, density of pine over density of water, 0.5 grams per cubic centimeter over 1.0 grams per cubic centimeter. Sg, 0.5. Similarly, the specific gravity of lead is 11.3 and of steel is 7.8. Specific gravity is useful as an identifying property of substances, especially solutions and other mixtures. For example, the condition of a lead-acid battery, such as those used in cars, is determined by the specific gravity of the battery's acid solution. A specific gravity of 1.27 indicates that the battery is fully charged, while a value of 1.12 indicates that the battery is dead. Geologic minerals can also be classified by their specific gravities, especially when their visual appearance is not distinctive.